Yeah, good morning all of you. Today examples on non-mechanical effects of current carrying conductor. Remember we have talked about the force between conductors, the current loops, torque, etc. Let us make use of all of them today. Now in the first example, see, the example says PQR, three long straight conductors. Currents are given to be 20, 10 and 30 by P, Q and R. The distances are also given in the data. P and Q parallel separation 2 cm, Q and R parallel separation 10 cm. Now the question is, find the net force on any of the conductors. For example, net force on P or Q or R like that. Now let us see. I will do one or two examples here. Now supposing if I take this conductor Q, let us consider now. For conductor Q to calculate the force, first consider the pair P and Q and the concept of parallel conductors carrying currents. The rule is, we have written force per unit length mu naught I1 I2 by 2 pi R, and the most important point is regarding the nature of the force. Parallel currents, attractive force, anti-parallel currents, repulsive force. Use that. Now here on Q, there are now two forces. Force due to P. See here, they carry anti-parallel currents. Therefore, they repel. This is the arrow I am writing. Please look for this arrow. Force on Q due to P is towards R is there. And that value is mu naught I1 I2. That is 200 by 2 pi. R is going to be 2 centimeter. 2 centimeter. This value used to be mu naught by 2 pi. The value is, yes, 4 pi into 10 that is minus 7, right? Then it is 2 into 2, 4, gone. So it is 10 power minus 7 and this is minus 2. Therefore final answer, yes, 200 into 10 rise minus 5 Newton per meter. Remember, in this case, most of the cases, we will be finding not the total force of the conductor, but force per unit length. Force per unit length, Newton per meter. And what is the direction? It is towards your right hand side. Similarly, let us calculate the force due to R. Now, Q also experiences force due to R. Again, when you consider the pair Q and R, one more time, anti-parallel currents. Anti-parallel currents. Therefore, this is what is the direction of force due to R. Force due to R. So this is how it goes. Whenever you want to find net force on a given conductor, look for all possible pairs. And most important point is regarding the direction of that force using the parallel currents or anti-parallel currents, and this happens to be mu naught by 2 pi. It will be 2 into 10 rise minus 7. I1, I2 will be like 300 in this case, and 2 pi. R is 10 centimeter. So this is 10 centimeter, 10 into 10 power minus 2. Yes, what will be the value? Oh, this pi is cancelled, right? Yeah. No pi term. Even no 2 pi. Yes, sorry. 2 into 10 power minus 7, 300 by 2 pi is already got the cancellation. Now here it will be like, this is 60, it will get right. 60 into, yes, 60 into 10 rise minus 5 Newton per meter. And look at these two vectors, they are anti-parallel. They are anti-parallel. Therefore, what is the net force? It is 200 minus 60 times, of course, there is a submultiple, Newton per meter. So this is 140 into 10 rise minus 5 Newton per meter. Any other kind of submultiple, if you can do, look for the options and find the right option. So this is how more than two conductors, of course all of them are straight conductors, finding the net force. Now the same question if I show with a difference, same data with a different question here, PQ are three conductors carrying currents IP, IQ and IR. I have named upward current, downward current and upward current I have shown here. Now let the distance between P and Q, the parallel distance between P and Q, R1, and that of between Q and R is R2. Therefore now the parallel distance between P and Q will be R1 plus R2. Now the question is that which of them can be in equilibrium? Here equilibrium means the static equilibrium which is caused by two equal and opposite forces. That is how we verify now. Now supposing if you take the condition for P condition you verify please. What do you observe? P is repelled by Q. P is repelled by Q and P is attracted by R. Why you see? Because anti-parallel currents, repulsion, and between P and R, parallel currents, therefore it is also, attraction. It is also attraction, yes. So P experiencing two forces which are in opposite directions. So there is possibility for P to be in equilibrium. Got the point? See, we are now verifying for the conditions whether it is possible for P or Q or R. I am verifying the conditions and I will write the condition. And that condition in mathematical form, whoever will satisfy that conductor will be in equilibrium. Now you see. Let us take the case of Q. Let us take the case of Q. In the case of Q, Q is repelled by P because of anti-parallel currents, and similarly Q and R again anti-parallel currents, again repulsion. So repulsion means like this. So again for Q also we find two forces anti-parallel, possibility for null point or possibility for equilibrium. Verify for that of R repelled by Q because of anti-parallel currents, yes, and R being attracted by P, we call it this direction. Now what is that we find? There is a possibility for P, Q, R, for any of them to be in equilibrium. Now which of them will be in equilibrium will be decided by the particular statement now we are writing. Supposing if I am writing it for P, there are two forces I am writing, and let me make it as equal, then only the equilibrium is possible. So for P if I am writing, between P and Q, what is that? Mu naught IP IQ by what is the distance between them? R1 is equal to force between P and R, which is mu naught IP IR by R1 plus R2, because between P and Q the distance is R1 plus R2. Therefore, if IP gets cancelled, now you are getting the condition IQ by IR is equal to R1 by R1 plus R2. If for this condition, remember P will be in equilibrium. P will be in equilibrium. Similarly, if you write a condition for R, the symmetry will tell you that IQ by IP is equal to R2 by R1 plus R2. For this condition, this conductor R will be in equilibrium. See, look at the currents. For the given currents, I am writing these conditions. That is, extreme conductors carrying parallel currents and the middle one carrying anti-parallel current. You remember this condition like that. Now, what about Q? For Q, yes, the condition will be, yes, IP by IR. IP by IR is equal to R1 by R2 condition you will get. Yes, this is for P, this is for the conductor R, and this is for conductor Q, which is the middle conductor. Again you see extreme conductors carrying parallel currents and the middle conductor carrying anti-parallel currents. Then there is possibility for any of the conductor can be in equilibrium. First point, any of them can be in equilibrium depending upon these conditions. Supposing we can have a case where all the three conductors are in equilibrium simultaneously, then we say the system is in equilibrium. System is in equilibrium. Like that. And that is possible when we have the entire system symmetry, carrying identical currents and separation being equal like that. So in such cases, each and every conductor can be in equilibrium. There is possibility and system is in equilibrium. Now you can do as a homework on your own that I take extreme conductors anti-parallel currents. See, anti-parallel. Your homework is I reverse the direction. And here I will make it as upward current or downward current. All different possibilities are there. So every time you have to look for parallel currents, anti-parallel currents. For the pair, draw the two forces and verify whether they are parallel or anti-parallel. So that is how we will come across such examples. See, this is the case of parallel conductors and force between parallel conductors. Same concept I have given as another question. What is that question? The question says, long horizontal wire P carrying a current of 3 ampere to the right. It is said that horizontal wire 3 ampere current to the right balances another horizontal current carrying wire Q. Q is also horizontal, placed at a distance of 5 centimeters below it. It means P below 5 centimeters. Mass of the Q is given to be 3 gram per meter. 5 current carried by Q. Like. Now, how does it know if I just draw a diagram with two simple lines for the entire data? It becomes so easy for us. What is that? Now, it is what is a long conductor, long wire. P carries a current I1 and that is given to be 3 ampere. It is going to be long wire. And another wire balanced below P. That is a very important point to be seen in the data. Whether that wire which is balanced in A is below P or above P. According to the data, it is below P. Supposing if I take this conductor as Q and it carries a current I2, we don't know whether they are parallel currents or anti-parallel currents, to be determined by using our principle. Now this parallel distance is given to be R, which is 5 centimeter. This is also a data. Now the question is that mg, any object balanced in A, mg should be balanced, and the balancing force for mg is always upwards because mg is always downwards. So the balancing force is always upwards. This is what is the balancing upward force. But now what is that balancing force? Means, see, it is the case of parallel conductor, both carrying currents. Therefore, F is equal to mu naught I1 I2 by 2 pi r. This is what is force per unit length. If L is the length of Q, if I multiply with L, that will be the total force on Q. Remember, mu naught I1 I2 by 2 pi r is not the total force in the case of parallel conductors. It is only force per unit length. If I have to get the complete force, total length on the conductor, this times length of the conductor under consideration. Now, remember, F should be upwards. F should be upward means now this force on Q should be towards P. For this towards P, now you see, what is that we observe? It should be a parallel current. Then only these parallel currents will cause attraction and thus F will be upwards. Therefore, as a simple hard rule, if the balanced wire is below the longer wire, they should carry parallel currents. And the same, if this wire which is balanced, if it were above the wire P, then they should carry anti-parallel currents. Let us remember this as a hard and fast rule. Right? Balanced wire below the given wire, it requires parallel currents. The balanced wire above the given wire, we require anti-parallel. Therefore, now here I am writing this arrow. After our discussion, this should be I2. Now, the famous condition, what is that? This mu naught I1 I2 by 2 pi r is equal to mg. Of course, I am sorry, into L is there. That into L is equal to mg. Now look at this data. The data says mass of the Q is 3 gram per meter, which is called as linear density. So the given data is not mass of Q, but it is mass per unit length. Therefore, shall I bring this L over here? Then this M by L is in the data as 3 gram per meter. So it's now all substitution. Mu naught by 2 pi, the value is 2 into 10 raised minus 7. I1 given to be 3 amperes, I2 required, R is given to be 5 centimeter, right? And M by L again given to be 3. Remember, it is gram per meter, therefore it is 3 into 10 raised minus 3 kg by meter times, let us consider G to be 10. So this will now give you the value of I2. I don't do that simplification, please do it that. Right, this is what is the current, and as I have told you, the direction of the current in the wire which we are balancing is very, very important. Options should not be confused by the student. Like this one. So again, the force between parallel conductors, but done as a different example of balancing in A. Now, same question you see. Again, I am telling you the force, parallel conductors, the same concept, but with a difference. A beautiful, intelligent question, one should say. Because one has to remember the concepts that we have discussed yesterday. Because after a conductor and parallel conductors, our topic was current loop in magnetic field. I have told you 3 to 5 very, very, very valid points to be remembered. Those concepts now, I don't explain straight away, I use in this example. Yeah, look at this example where we are using 3 to 4 important concepts. It can be either a conceptual question or it can be a question based on numerical, asking for the net values also. Now here the question is, why is a straight conductor, long straight conductor, fixed conductor, and ABCD is a loop, a square loop of side I, and it carries a current 2I, and it is given to be in anti-clockwise sense. It is given in the data. Now the question is that, and both are held in the same vertical plane such that this parallel distance is L by 2. Remember, we are doing this example for both of them held in the same vertical plane, right? And this distance is L by 2. Now, as I have told you, it can be variety of questioning from this data. Let us see one after the other. The first one is whether this loop ABCD, which is free to move, it is given to be, what type of motion it acquires, whether it is translatory or rotatory, or it is possible with both the cases, or else what is the net force or what is the net torque, so on. It goes. Therefore, now let us calculate the force first. How we calculate the force? Because each and everything, now first let me take this current direction, anti-clockwise given to be, and this current is 2I. Now here we can find the 4 straight parts, AB, BC, CD and DA, 4 straight parts. In those 4 straight parts, let us take a pick. First we take this AB and CD with respect to Y. Then what we find is this long wire and AB parallel currents. That F equal to ILB sin theta only, but when we have used that and also then the mechanical effect, the force, we got that parallel. The same I will use here straight away our result. So AB experiences a force which is repulsion because of anti-parallel current. See, this I will write it as F1, which is on this AB. So force on AB is equal to mu naught I1 I2 by 2 pi r. This force per unit length only I am writing. Therefore, this is what is mu naught. I1 I2 means 2I square, and what is the distance between them? L by 2. Therefore, this is 2 pi times L by 2 into, what is the length of the conductor now? Here it is L. That is what is the force. So which will get it as, yes, L gets cancelled, 2 gets cancelled. Therefore, it is mu naught I squared by, this 2 is the right, 2 mu naught I squared by pi. And what is the direction? It is away from Y, because it is a repulsion that is experienced. Similarly, let us write for one more straight part, which is CD. Now when you find this Y and CD, as the currents are now parallel currents. Parallel currents, therefore force, I am writing it on CD. Force on CD is equal to mu naught, again 2I square by 2 pi. What is the distance between these two? L and L by 2. Therefore it is 3L by 2 times L. So again this value is, yes, 2 gets cancelled. So this is 2 mu naught I squared by 3 pi. Mu naught I squared by 3 pi. And this is towards Y. Why? Because see, these two are parallel currents. Attraction result will give you towards Y. Now let us calculate what will be the case of this BC and DA. For that we have to use that effect what I have said. First, you see here, this is what is the force, upward current, and remember we are writing the average value of B on BC and DA because it is variable field for the distance, right? Average value. So if we consider this is inward field at BC, similarly at AD also it is inward field. Now let us use that F equal to ILB sin theta and Fleming's left hand rule. Fleming's left hand rule, you see, current inwards, current is from, field is inwards, the current is from C to B, that is towards what? Left hand side. Look at my thumb is downwards. Thumb is downwards. See, that is why in this topic, this unit as a whole is such a difficult thing for students, because they don't use this right hand and left hand. If you use that, very simple answers. Now similarly, what we take on AD, use our left hand rule, it will be like this. And remember, these two forces will be equal because induction same, length same current, and also they will be on the same line joining. That is what now I am writing. So force on CB, force on BC is equal to force on DA. They are same, and if I write minus F dA bar equal and opposite, same line of action. Same line of action. What does it mean? Net force anyway happens to be 0 because equal and opposite. Since they are on the same line of action, no couple also. So here no couple is formed. No couple is formed means no torque. No torque means no rotatory motion. So finally we are left with only the net force. So what will be the net force? So this net force is this mu naught I square by pi, mu naught I square by pi, common because they are anti-parallel. They are anti-parallel. Therefore I will take all the summation as, so this is mu naught I square by pi times 2 minus 2 by 3. So this is what is 4 mu naught I squared by 3 pi will be the answer. And what is the direction? It is, remember, this is repulsion and this is attraction, which is more. This repulsion is more than this attraction because of larger distance. So final answer is away from Y. That is towards your right hand side. So no question of torque, no rotatory motion, but it experiences net force, and hence there is a translatory motion in a particular direction depending upon the order of the currents given in the loop. Now the case of current loop placed in a uniform magnetic field. Yesterday again we have given a good number of concepts. Look at this example. PQRS is a loop in the form of a trapezium. It is in the form of a trapezium, right? And it is placed in a uniform magnetic field. The field is said to be inwards. Now the forces are shown. Forces on this face F1, F2, on this side it is F3. Now the question is, find F4. You remember what was our first statement in the case of a loop placed in external magnetic field. We said we are taking the case of a rectangular loop and the results are valid for any other shape also. In such case, the net force on the loop was 0 if it is a uniform magnetic field. uniform magnetic field, net force is 0, but there will be net torque due to a couple. But now here, net force is 0 is applicable even for this geometry. That will be the key and solution for this. How? You see. Suppose if it is not given, let me take this angle as some theta. Then I am resolving this F4 because this F is always just normal to that while So if this is what is F4 that I consider, now this F4 I will resolve into components. Yes, this is one component and the other component. Since this is theta, this component is theta, therefore this is F4 cos theta and this one is F4 sin theta. Yes, now I take this. We don't require the theta also. So this is what is the first step, resolving F4. Now since net force is to be 0, for the net force 0, what is the condition? See, let us take this as some x-axis and this is some y-axis. First I am writing along y-axis, suppose, then what should happen? That F4 cos theta should be equal to F2. So these are anti-parallel. If they become equal along y direction, net force will be 0. So F4 cos theta is equal to F2. Similarly, now what is that along x-axis? You have F1 and F3 anti-parallel. Therefore, along x-axis this one is F4 sin theta, F4 sin theta, which is along negative x-axis. Therefore, the other should be I am taken as F3 minus F1. Why F3 minus F1? Because this is along negative x-axis. These two should give a resultant along positive, and thus net force becomes 0. So I am writing for magnitudes here. Please do remember, I am not writing for vectors, only for magnitudes. F4 cos theta is equal to F2. Next one is F4 sin theta is equal to F3 minus F1. Right? And this is what is the answer. Now we have two equations. Square them and add them. Let us square them and add them. Both the expressions squared. Therefore, F4 cos square theta plus F4 sin square theta will be as F4 squared is equal to, yes, squaring and adding, plus F3 minus F1 whole square. Therefore, our answer is F4 under root. We are writing it as F2 squared plus F3 minus F1 squared. So that is how we have used the concept of net force on a current loop in a uniform magnetic field is 0. Look at this solution. All the solutions, whenever I have told you that we should be good at our fundamentals. Even those fundamentals we are now giving as a tidbits every day. I am not simply coming and doing some examples. I am brushing all the concepts and then we are doing these examples. Remember, and also good number of models are reaching you every day. Assignments are shared. One more time I request you on behalf of your parents, because we all love your parents a lot more than you, and that is why please go through those assignments. Good number of examples are there. Your examination, very easy examination. Remember, we have told many times, you are all going to write very easier examinations. Because your classroom and your notes, your examination papers, assignments helps you a lot. I am telling you, they are all more than sufficient for the challenge of your exam. One more time, one example I showed here. Here again, I would like to use a concept of vector only. We have told about magnetic moment of a loop. Any current carrying loop acts as a dipole and hence magnetic moment. Now here I have given a geometry. Of course there is symmetry for easy calculation. See here. This one is a symmetry. This one is a symmetry. 1, 2, 3, 4 parts are there here. All these 4 parts are said to be semicircles. Semicircles of diameter A. Semicircles of diameter A. So these are 4 semicircles connected to form this loop. Remember, A is not the radius. I told this is what is the diameter, which is A. This is what is the diameter A. And it carries a current. This loop carries a current. look at the direction of current also, order of current, which is more important in the case of finding magnetic inductions and finding magnetic moments as well. Now I have given this in clockwise. See, this is what is clockwise and anti-clockwise order of current I have shown. First, now the question is find the magnetic moment vector, because it is said this loop is in xy plane. Remember, the data says this entire loop is in xy plane. Find m bar of the loop. M bar of the loop is the required thing. Definition is very simple. For any loop, moment m is equal to simply current times cross section. Current times cross section, I is given, and now what about A? To find the area of the loop. Now what is that area you find? Area is 4 times area of semicircles plus area of the square which is formed in the middle portion, right? 4 semicircles, that area, plus the consequence, this middle part becomes a square, this one. So this is 4 times, right? What is that area? You tell me. Area of a circle is pi r square, therefore it is pi r square by 2. Therefore it is pi r square means, yes, a square by 4. Remember why a square by 4? Because the radius is not a, but it is a by 2 square. A squared by 4. Half of that, therefore it is 2. Half of that. Pi a square by 4 for each semicircle. Pi a square by 4, half of that. Such 4 parts are there into 4. Next one is, of course, pi. This one is a and a square, area a square. This is simply a square. So what is the answer? This is pi a square by 2 plus a square. This is 3 pi a squared by 2. See, now if I am writing this as a magnitude, it is 3 pi a squared by 2. Is that okay? 4 cancel, 1 by 2 plus 1 and so on. Right, this is a square times pi by 2 plus 1. Yes, pi by 2 plus 1, the magnitude. But now here I want it as a magnitude. And I have told you what is the magnitude? Direction also. We want direction. What is the direction of A cap? Always we are told A cap is outward normal. Outward normal. If this is the plane, which is xy plane, outward normal is towards U, that is z axis. The positive z axis you get. Therefore, I will write it as A bar is equal to, here I will write K cap. K cap. So the final answer is m bar is equal to simply I times A. So this is A square I into pi by 2 plus 1 K cap. So here we have done 3 cases. First one is finding areas of a given geometry, then writing areal vector, and number 3 finding the moment. Likewise, any example that we did, actually you can see it will be consisting of 3 or 4 examples. Every time I have told you, you just stay at your answer for a while. What is the answer and what is the data? Correlating the result with the data. And then we thinking, supposing, what all changes possible in the data, then how this result will have a change. Supposing if we are able to think on these lines, we never encounter so-called new question, at least in NEET and CET. Maybe in JEE mains or advanced it may be the case, but in CET examples, NEET examples, this habit of understanding the result and correlating with the data definitely makes you very good at your solutions. See, here is a brief discussion about a very big topic for our competitive examinations, moving coil galvanometer. I will just make it as quickly as possible. Go through each and every statement, and each and every statement is a solution for your NEET CET question. First one is the principle of moving coil galvanometer. It works on the principle of current, torque experienced by a current loop in magnetic field. The tau is equal to NIAB sin theta. What we are told is the principle of the moving coil galvanometer. Now, you know about the description. It has a coil. coil with number of turns, then it is suspended between magnetic poles. Now we are discussing about the specialities in the design, not about the entire design. We are now discussing the speciality. First, the specialty is about the coil. Regarding coil, actually a copper wire which is laminated copper wire is wound on a non-magnetic frame. Remember, it is not a magnetic frame, non-magnetic frame. A laminated copper wire is wound. This is one special, non-magnetic frame. And second one is that inside the coil, a ferromagnetic piece like iron or cobalt is placed to enhance or to maximize the flux through the coil, and hence the torque of the coil is also, torque on the coil is also maximum. So these are the two specialties for coil. Now regarding suspension. See, the coil is suspended from a rigid support such that now this coil will actually deflect due to the torque. Tau equal to NIAB will cause a deflection in the torque. Therefore now the suspension wire should withstand load of the coil, because coil is a bit heavier. It has to withstand load of the coil, and also due to deflection the suspension coil will get a twist because of action-reaction nature. Therefore now the suspension wire should withstand, number one, load of the coil, number two, twist in the suspension. Because of that, it should have high Young's modulus and low Poisson's ratio. Remember, coil should have higher Young's modulus and lesser Poisson's ratio, and that is why the preferable substance material would be phosphor bronze suspension in the case of moving coil galvanometer. Now regarding magnetic field. Now for the magnetic field here, we don't apply an ordinary magnetic field on this coil. Rather, magnetic field is what is called as a radial magnetic field. Remember, the magnetic field in the case of moving coil galvanometer is radial magnetic field, and it is produced by concave shaped poles. Concave shaped poles, because if you remember your design of these are the magnetic poles, north pole and south pole, in which we are suspending the coil. Remember, these are not flat poles, these are concave shaped poles to produce radial magnetic field. Why produce? What is the specialty of radial magnetic field? Why only this radial magnetic field? Means this, when we write the condition tau is equal to NIAB sin theta, it always keeps sin theta is equal to 1 for any orientation. For any orientation of this coil, sin theta is equal to 1. That is, plane of the coil is always in the plane of the magnetic field. Condition is satisfied, and that is why sin theta is equal to 1. This becomes maximum torque tau is equal to NIAD. So torque remains to be maximum and uniform throughout for any orientation. Concave shaped poles, radial magnetic field. Now here comes an all important formula for moving coil galvanometer. Keywords: moving coil galvanometer, current measurements, right? Current sensitivity, voltage sensitivity. You remember figure of merit. Now we discuss that. Now NIAB is the torque produced in the coil, whereas C theta is the restoring torque produced in the suspension. And this C, remember here N refers to number of turns in the coil, A refers to cross section of the coil, B refers to magnetic induction produced by these pole pieces. Now C refers to suspension. C is called torsional constant, otherwise called as restoring couple per unit twist. So this is couple per unit twist of the suspension wire. Now in the equilibrium, action reaction equal will make NIAB is equal to C theta. This I is equal to, we have given this expression. So this is what is I proportional to theta, is what is the I is equal to K theta, the principle of moving coil galvanometer. Here you see, supposing if I write I is equal to K theta, K the galvanometer constant is C by NAB. Please do remember, galvanometer constant depends on if the parameters change, how the constant changes. Look here. It depends upon C, the couple per unit twist of the suspension. It depends upon the number of turns and cross section, that is size, and as well as number of turns of the coil. B, the external induction. It depends upon all the parameters that we have shown there, right? And now theta by I is what is called as sensitivity of current. It is sensitivity of current. So sensitivity of current, what is the expression you get? Theta by I is equal to NAB by C. NAB by C. So how to increase the sensitivity of the current? Remember, the sensitivity of the current refers to the least count of the device sensitivity, and which is always reciprocal to, which is always inversely proportional to the range of the device. Range, the maximum value that we can measure. Here we are writing theta by I, the current sensitivity. Supposing I am told to write the reciprocal, I by theta is C by NAB, and this is called figure of merit. This is called figure of merit, otherwise called as the range of the device. Range of the device. So this is what is the most important thing. Now see how to increase the sensitivity of the device, how to increase the range of the device is essential thing. Now in the same thing, what I would like to show is that suppose theta by I is current sensitivity. Sometimes you are asked for the voltage sensitivity, the sensitivity of voltage. Then what is that? Theta by I times 1 by G. If G is the internal resistance of that device, this I into G will give you the voltage. Therefore, what is that we are doing? Current sensitivity. Yes, current sensitivity by internal resistance. Internal resistance will give you sensitivity of voltage. Sensitivity of voltage. Please remember, it is not multiplying with internal resistance, but it is 1 by internal resistance of the current sensitivity is giving you voltage sensitivity. Whereas in the case of figure of merit, if I am writing it as figure of merit of voltage, figure of merit of voltage, it will be, yes, figure of merit of current, figure of merit of current into capital G. Here you get current sensitivity upon the internal resistance of the device. Whereas when it comes to the figure of merit of voltage, it is internal resistance multiplied with the figure of merit of current. All these are very popular topics for your NEET and CET. Please follow them carefully and do your assignments. Have a good day.